Hello everyone. In the last class, we discussed about different measures of an earthquake, which are magnitude and intensity. We also learnt how magnitude and intensity are affected by different factors. In this class, today we will develop an understanding of how different past earthquakes have caused damages and how we have learnt lessons from those observations. To start with, let us look into some of the notable past earthquakes. This slide contains list of a number of earthquakes from around the world which have been instrumental in this slide contains list of important earthquakes that have happened across the world. What we will do in this class, we will look about each of these earthquakes one by one. We will see about their sources, we will see about the observations during the earthquake, and we will also note or record the lessons that we have learned from various observations during these earthquakes. Let us look into 1906 San Francisco earthquake. An earthquake of magnitude 7.9 with a maximum intensity of 11 on modified Mercalli intensity happened in the San Francisco region. The earthquake was triggered by rupture of San Andreas fault. The rupture happened over a length of 296 miles. This happened at a strike slip fault at the boundary of Pacific and North American plates. The epicenter was located 2 miles west of San Francisco in the Pacific Ocean. The intensity of the earthquake was 11 on modified Mercalli intensity scale in the San Francisco city, which is perceived to be very high, and therefore the losses have been tremendous. 3,000 people lost their lives and over 80% of the San Francisco city was destroyed. $500 million worth of damage also happened. There are furthermore observations from the San Francisco earthquake. For instance, the two plates had a relative sliding of up to 21 feet. During the earthquake, there were incidents of fire happening from electrical power lines and broken gas mains, and due to broken water pipelines, the unavailability of water to curb these fires caused even more destruction. There are several lessons that we learn from this earthquake. For instance, the expansion of fireproofing zones in San Francisco happened after this earthquake. The city also adopted a high pressure underground water supply system. The first building code in 1927 included seismic design criteria for California. There was also formation of organizations like Seismological Society of America and Structural Engineers Association of California. And because of all these lessons that we learned from the observations during the earthquake, the outcome was that when the same region was hit by another earthquake in 1989, the 1989 Loma Prieta earthquake, the buildings exhibited better performance and the damage was limited. Moving to 1940 El Centro earthquake. Please note that the previous 1906 San Francisco earthquake happened when there was no Richter scale. So the magnitude variation for the 1906 San Francisco earthquake would be far more. By this time, Richter scale had come into picture. So the magnitude of this El Centro earthquake was measured to be 6.9. At the same time, the maximum intensity was perceived to be 10 on a scale of 1 to 12. This earthquake was also a result of rupture of Imperial fault, which is again a strike slip fault. The epicenter was located 5 miles north of Calexico in California, and relatively lesser losses were observed during this earthquake in terms of number of lives lost and number of buildings damaged. There are further observations from the earthquake. It was the first earthquake where we have a recorded seismograph close to epicenter, and that's why this ground motion is still widely used in seismic design even today. Further on, many foreshocks and aftershocks were observed during this event. Foreshocks refer to ground shaking which happens before the event, and aftershocks are earthquakes or ground shaking which happen after the main event. So many of them were recorded, and that's how the concept of foreshocks and aftershocks was established as well. Again, there was a surface rupture of 40 to 60 kilometers, much lesser than the 1906 San Francisco earthquake. Coming to 1967 Koyna earthquake which happened in India. So it happened very close to Koyna dam, within 5 kilometers of the dam. The dam had been built between 1955 to 1962, and the earthquake happened in 1967. That's how some people perceive that it was probably triggered by the reservoir. The magnitude of the earthquake was 6.3 and the maximum intensity was perceived to be 8 on modified Mercalli intensity scale. The energy released was equivalent to Hiroshima atom bomb, and in this case over 200 people lost their lives and few thousands got injured. The Koyna dam also suffered some cracking, and there was fissure observed in ground as shown over here. So this is 10 to 15 centimeter wide fissure which happened over 25 kilometer length. But the major observation was that there was an earthquake which happened in Deccan Plateau, which was earlier considered to be aseismic, or which was considered to be safe from earthquake. This gave rise to the possibility of intraplate earthquakes. This is one of the intraplate earthquakes that has happened. Most of the earthquakes, as we have seen in previous classes, are interplate earthquakes. This earthquake further propelled a study of reservoir induced seismicity, and there was a revision of seismic zone map of India where regions in zone 1 were moved to zone 2, and Borehole Geophysics Research Laboratory BGRL was established at Karad in Koyna to further look into seismology of the region. And the major outcome of this of these lessons from Koyna earthquake is that we have improved seismic design practice in our country. Let us look into 1985 Mexico City earthquake, an earthquake which happened roughly 350 kilometers away from Mexico City. The epicenter was located in Pacific Ocean off the Mexican coast, and this happened at a convergent plate boundary, which means that Cocos plate and North American plate, these are colliding with each other, and this led to the 1985 Mexico City earthquake. The magnitude of the earthquake was 8.0 and the maximum intensity was perceived to be 9 on modified Mercalli intensity scale. And in this earthquake, at least 5,000 people lost their life, and $5 billion worth of damage also happened to the property. During this earthquake, the observation was made that buildings with around 20 story, which had natural period of roughly 2 seconds, suffered the most of the damage, while the other buildings with lesser height remained intact. These buildings collapsed. The second observation was that the damage was concentrated in Mexico City, which is located 350 kilometers from the epicenter. The damage was much lesser in places close to epicenter. What does this mean? So we learnt lessons from these observations that local soil conditions affect seismic response of structure. So what happened is that Mexico City, which was located on alluvial river bed, the river bed filtered the seismic waves, and the seismic waves which reached the Mexico City had only few frequencies which were predominant. The buildings which had their fundamental natural frequencies close to the predominant frequency of the seismic waves collapsed. So those were the 20-story buildings having natural period of 2 seconds. So from this we understood that the local site conditions as well as the soil structure interaction affect the seismic response of building structures, and these effects started to enter our seismic design practice beyond this earthquake. Then we have 1989 Loma Prieta earthquake. Remember we mentioned it during the 1906 San Francisco earthquake. Both happened due to the same fault, that is the San Andreas fault. So this is a strike slip fault at the boundary of Pacific and North American plates. In this case the magnitude was little lower at 6.9. The maximum intensity was perceived to be 9, which is lower than the San Francisco earthquake, but it was still the most damaging earthquake in the region after 1906 San Francisco earthquake. The major observation during the earthquake was that the peak acceleration went up to 0.65 G at the epicenter, which is relatively very high. In this case there was loss of lives and property as well. Further, during this earthquake a number of landslides, roughly 4,000, were observed around the region. There were also collapse of Cypress Street viaduct, and soil liquefaction was also observed at many sites. And prior to earthquake, some magnetic disturbances were also reported by a sensor placed 7 kilometers away from the epicenter. So from all these observations, what do we learn? First thing is that we learn that we need to assess our design and construction procedures. This is coming from the collapse of Cypress Street viaduct. We also need to adopt ductile detailing in the structure for seismic resistance. Another thing which we learn from the observations including landslides and soil liquefaction, that the local geology and site soil conditions can aggravate the damage. And further on, we also find that social problems challenging efficacy of emergency response were identified. So from this earthquake onwards, the effect of local site conditions and ductile detailing became integral part of seismic design practice. Further on, many attempts to predict earthquake based on some magnetic disturbances were also initiated after this earthquake. Moving to 1994 Northridge earthquake, the magnitude of this earthquake was 6.7 and the peak ground acceleration of 1.82 G was recorded, which is very high. The source was a previously undiscovered fault, which was later named as Northridge blind thrust fault. So it is again a thrust fault which is happening at a convergent plate boundary. The epicenter was located 20 miles northwest of downtown in Los Angeles, and over 60 people lost their lives and more than 8,700 people were injured. In this case, a number of observations related to open ground story buildings were made, which performed poorly during the earthquake, and many casualties happened in multi-story wooden frame buildings, and numerous fire incidents from broken gas lines also occurred. So from here onwards, there was a need to revise seismic codal provisions, and ACI 318, which was thoroughly revised after this earthquake. We also understood from the failure of various open ground story buildings that stiffness and mass irregularities jeopardize structural response, and these should be minimized. We will learn about these stiffness and mass irregularities in the upcoming class. We also started to use more computer simulations in seismic design process, and this ground motion, that is the 1994 Northridge earthquake, is also one of the widely used ground motion in seismic analysis and design. Let us look on 1995 Kobe earthquake in Japan. So the magnitude of the earthquake was 6.9 and the maximum intensity was as high as 11 to 12 on modified Mercalli intensity and 7 on JMA, Japan Meteorological Agency scale, which is from 1 to 7. So the maximum intensity was the highest, and it is the Japan's deadliest earthquake after 1923 Great Kanto earthquake. This also happened at strike-slip fault at boundary of Eurasian and Philippine plates. The epicenter was located at northern end of Awaji Island, roughly 20 kilometers from the Kobe city. Now, by this point, you might have realized that most of the deadliest earthquakes happen due to movement at a strike-slip fault, that is the transform plate boundary, and the other earthquakes happen at convergent plate boundary. So, which is very much similar to what we have learnt in the previous class. In this case, the loss of lives and property were also very high. A number of buildings, elevated roads and rail bridges suffered damage of serious scale. There were numerous liquefaction and lateral spreading happening around the region. Around 300 fire incidents also were triggered, which is due to broken gas pipelines, etc. And water, electricity and gas supplies got disrupted, which also hampered the rescue operations. So, from all these observations, what we learnt that this was a wake-up call for Japanese disaster prevention authorities. They finally ended up evaluating seismic design codes and they revised these codes further. Some of these buildings and elevated roads including this Hansin Expressway, as you can see in the figure over here, where 18 consecutive piers collapsed. So, all of these also give indication that insufficient transverse steel reinforcement can lead to brittle failure. So, there was shear failure of these piers as well. And there was also evidence of soil structure interaction playing a role in that failure. So, the outcome of all these lessons was that a number of factors add to seismic vulnerability of any structure or a region, which include population density, dense transportation network and poor soil condition. Let us look into 2001 Bhuj earthquake, which happened in Gujarat, and the epicenter was located 9 kilometers southwest of Bhachau in Kutch region, and this happened due to rupture of a previously unknown strike-slip fault, and this was also intraplate in nature. The magnitude of the earthquake was 7.6 and the maximum intensity was perceived to be the highest, that is 12 on modified Mercalli intensity scale. There was widespread damage to buildings and loss of lives. Around 20,000 people lost their lives and almost 2 lakh people were injured. Over 3.5 lakh buildings were irreparably damaged, which means they are beyond repair. There were a number of observations during the earthquake. Open ground story buildings performed very poorly, as you can see in these photographs that open ground story just collapsed. Buildings with heavy asymmetric mass suffered major damages. So, in this figure you can see that the rooftop water tank actually got separated from the building and there was a lot of damage related to this. So, this also means unanchored heavy masses such as water tanks got dislodged. From this earthquake observations, we have learnt a lot of lessons. The first thing is that, very similar to previous earthquakes, some of the previous earthquakes, stiffness and mass irregularities should be minimized. We will learn more about these irregularities in the upcoming class, so that we can avoid these irregularities. We should also adopt a practice of mock drills, basic first aid and CPR, so that we can have required post disaster rescue operation. After this event, Gujarat State Disaster Management Authority (GSDMA) came up with handbooks for earthquake behavior of structural as well as non-structural elements. These come from a number of experts in earthquake engineering community, and therefore they have been very instrumental in seismic design practice after this earthquake. This earthquake also paved way for mainstreaming of earthquake engineering research and education in the country. Let us look into the most recent earthquake, which is the 2015 Nepal earthquake, which happened from the main Himalayan thrust, and the epicenter was located between Kathmandu and Mount Everest, close to the Nepal-China border. The magnitude of earthquake was 7.8 and the maximum intensity was perceived to be 10, and it is the worst natural disaster in Nepal since 1934 Nepal-Bihar earthquake. A lot of people lost their lives and a number of buildings, almost 6 lakhs buildings, were damaged. There were a number of observations from the earthquake that we had experienced a lot of foreshocks and aftershocks. We also observed widespread and severe damage to unreinforced masonry structures, including monuments and heritage structures, including dharara. So, from this we learned that we need to have a control on the structural typology of the building. We have seen damage to unreinforced masonry structures. So, we need to think about what kind of structures we should build in future. And we should also look into the conservation of heritage structures as well. Then entire villages near the epicenter got flattened out. A number of vehicles got crushed due to landslides triggered by the earthquake. There was bursting of a glacial lake, but it is not sure that whether the earthquake triggered it or not, but it happened very simultaneously with the earthquake. So, a number of lessons learned from these observations are there. We need to consider repair and reconstruction of monuments seriously so that they do not get affected in future earthquakes. We also need to have policy, technology, tools and skills so that we can adopt requisite post-disaster rescue operations to eliminate any casualty during these earthquakes. We also need to update the Disaster Management Act and strengthen our rescue operations. The outcome was that National Reconstruction Authority was established as an independent authority, and research on safety of masonry and heritage structure got an impetus worldwide after this event. So, we have gone through a number of deadliest earthquakes happened across the globe. We have seen the observations related to damage to buildings especially, and we have also learned a lot of lessons from all these earthquakes. With this, we have also moved to a better seismic design philosophy and seismic construction philosophy. So, the general remarks from all these earthquakes is that today we need engineered structures. We need to design our structures well so that they do not collapse, and thereby the loss to lives is also minimized. We need to do proper seismic design and detailing, and we need to further enhance our understanding of seismic behavior of buildings through earthquake engineering research, and we should be able to develop technologies to eliminate or mitigate losses due to earthquakes. Thank you.